All right. Oops, there we go. All right. So hope you guys had a good snow day. At least got maybe catch up on work. I don't know how overwhelmed you are. Throw up just kind of a quick overview of the week. And hopefully I'll stick to it this time. We'll see. Today we're going to go through the section of your notes 1.5, which is primary productivity. Then tomorrow I'm going to give you guys, it's like a video of somebody doing the lab, and then you're going to kind of take their data, their information, and analyze it, because it's not one that we can really efficiently do, but it's still important and does involve a tiny bit of math. Thursday, we're going to be watching just bits and pieces of a documentary about coral reefs, and then end on some notes. On Friday, this is probably the biggest part of this unit. It's like all of ecology wrapped up into one.
Wow.
And then we'll move on to the next unit. So your packets will be due in roughly about, I would say, a week and a half. So your note packets will be due in about a week and a half. So keep that in the back of your mind. Any questions on the nitrogen stuff or any of the stuff from last week before we get moving?
No.
All right. So this is the spot you should be in your packets. There is a partial FRQ for nitrogen that you'll end up doing. It's only a tiny part of it, so it's not too bad. But just kind of rehashing, and then we're going to start on this part once I get my PowerPoint pulled up. Like I said, I'm having to work off one of these senior computers, and I hate it. And I've lost my touch screen, and I'm sad.
Yeah.
All right, PowerPoint. Maybe. There we go. All right. So, like I said, we're going to be talking about what's called primary productivity. So, if you missed and have dreams about the photosynthesis unit from biology, we're going to revisit it for a little bit. When we're talking about primary productivity, it's usually a rate. Sorry, I should probably get that up there for you. It's usually a rate of how fast is photosynthesis working, as opposed to an amount. So productivity is a rate. Sometimes it does get referred to as amount, but how much energy or how much mass is being produced instead of how fast it's being produced. And again, when we look at energy from a plant perspective, we're looking at glucose.
You said the rate at which photosynthesis is what?
The rate, what did I say? Rate at which photosynthesis
works as
create glucose. We'll put it that way.
Okay.
So how much energy or how much mass of glucose is being made.
Okay. Thank you.
You're welcome. All right. Am I good to go on?
Yes.
All right. No arguments? All right. So there's a couple different terms. The first one is gross primary productivity. It's abbreviated GPP, or it gets referred to as gross. Just kind of like if any of you have ever looked at a paycheck, you get a gross and a net amount. the same thing is going to be for this, for primary productivity. So gross is the total amount of production of biomass. On a paycheck, it would be the total amount that you made, whether or not it's the taxes the government takes from you or the actual stuff you get to spend money on. It's just the total amount. All right. The next one is called net primary productivity. That is the rate of production of biomass potentially available to consumers or herbivores or omnivores. This, as far as the paycheck analogy goes, this is how much actually gets deposited into like your pocket, into your checking account, your wallet, whatever. So you have the gross, which is the total amount, and then the net is what you actually take home. So with this, gross is still the total amount, net is the amount that's available to eat or produce.
Mm-hmm.
So in regards to like where does some of this stuff go, we know we pay federal, state taxes in our paycheck, but as far as plants go, some expenses, I guess that you could say, the sugar doesn't, or the glucose doesn't always go towards being 100% edible. It's got to do cellular respiration as well as photosynthesis. Remember, plants have mitochondria too, even though they primarily run off of their chloroplasts, which do the photosynthesis. But plants do cellular respiration as well. So they need that glucose, that sugar, for their own cellular processes. The glucose is for food, but then they also use it to keep themselves going too. So that's going to be the major differences between gross and net. All right, this is where I said a little bit of math comes in. So you have your pretty little sun up here in the corner. There's my mouse. All right, sun helps a plant like this stupid dandelion go through photosynthesis. And it creates this whole gross amount of like glucose and biomass, but some of that gets taken away for cellular respiration, which is what that R stands for. And then that will give you the actual amount that's usable. So again, this is just kind of repeating what I said before. Some of the productivity is used in the autotroph's own processes, like cellular respiration. This also gets lost as heat, just like it does with us. So you're going to see this equation a lot. The NPP equals GPP minus R. And you thought X and Y were a lot.
Don't move on.
Everyone good?
Not yet.
Okay. And just as kind of a refresher, if I haven't said it before, when I talk about biomass, that's like plant parts, like the leaves, the stems, the flowers, anything that's part of the plant, the roots, stuff like that. So biomass is all of it.
Wow. Okay, I got it.
All right. So units, because you know units are super important. Everything needs to get labeled. When we talk about energy, ooh, there it is. When we talk about energy, it's in a per unit area per time. So you have an example of joules per meter squared per year. Oops, sorry guys, I didn't mean to do that. All right, so joules is a measurement of energy. You could think of like watts, like light bulbs, and we talk about them in watts or kilowatts. Joules is just another measurement of that energy. Meters squared, meters roughly 3 feet. So think of it that way if you need to, and then per year. So energy, space, time. When we talk about biomass added per unit area per unit time. So this is where it comes in as grams or kilograms, things like that, meters squared per year. These are all, remember, it is rates. So this is how much is being done per meter square per year, or how much is being added per meter square per year. Like a miles per hour is a rate. Is everyone good? This is a fairly short PowerPoint, so hopefully it's not too bad.
Yeah.
All right, so looking at this graph, you know at least NPP, GPP, the R remembers respiration. Sometimes you'll see it with that subscript, but when you see the big R, it's the respiration. It's the stuff that's being lost due to cellular processes and heat. All right, so take a second to look at this graph and tell me what you see in it. Give me some observations.
Forest age, annual carbon, and I see both NPP and GPP in there, and I see R to the A, or whatever that is.
Yeah. All right, so it shows a graphical version of the formula that you just did. What does that gray area represent?
It represents the NPP, the net productivity, or primary productivity, or hang on, let me go back. Net primary productivity.
So you've got your gross all the way down here. You've got your respiration down here. That means that this is the functional area. This is stuff that's getting lost for cellular respiration, whatever. This is the stuff that's usable. Okay. Now what happens as a tree gets older?
It releases carbon dioxide.
It releases carbon dioxide whether or not it's young or old.
Okay.
As far as productivity and carbon flux, so
I'm guessing the processes slow down.
they can. So this one we're looking that it has like a optimal age for a forest when the GPP. Okay, that's a lot of P's. Hold on. GPP peaks compared to the respiration rate. So that would be this area right in here. You see that a whole bunch of carbon influx.
Mm-hmm.
And then that creates more usable NPP. Leave it there. Why would that happen? See how many of you guys remember photosynthesis. What do the plants need to intake?
Oxygen.
No. Good, Devon's got it. Carbon dioxide. They take in carbon dioxide the same way that we take in oxygen. Okay, so when you have this bigger flux of carbon coming in, you've got a bigger flux of usable glucose, or your NPP, or biomass, or energy, however we want to put it in that specific scenario. After that big influx, that GPP decreases and then kind of levels off. and it becomes steady throughout the rest of its life. This is kind of when you would see an ecosystem kind of reach an equilibrium. I believe one of your assignments last week or the week before, I forget, asked, yeah, it was last week because it was nitrogen cycle, asked why does an ecosystem, or something about how does an ecosystem that has no human influence adjust for like nitrogen? And they learn to create like an equilibrium within that ecosystem. So that way everything just kind of balances and there's not a whole lot of excess, but there's not a whole lot of shortage either. So pattern between even nitrogen cycles or respiration of plants. All right, so some factors that would affect primary productivity. I'm just going to put them all up here because I'll forget if I don't. Solar radiation, so the quality and the quantity of light, which probably seems like duh, plants need light to grow. It's part of photosynthesis. But how good that light is, how direct that light is, too much, too harsh, depending on the plant's zone of tolerance. Which we went over, did we go over? Oh no. That's next unit, sorry. So zone of tolerance being like the areas that it can function, but at either extreme, it's going to die off. They're going to struggle and then die off. Temperatures in general, warmer temps correlate to more productivity. So if we tried to plant some plants outside right now, they're not going to do too well. We're getting plenty of sun, plenty of carbon dioxide, some water, but the temperature, it's going to be too cold. All right. Do you guys remember this from biology, denaturing? What that is? I'm going to go with a big fat no. So there's enzymes in your body, enzymes in every living thing, and when they get denatured, it's like getting misshapen. So enzymes are like puzzle pieces. In order to work, they have to find their perfect little match and hook together. And once you kind of deform that enzyme, they don't match up anymore and they don't interlock in order to produce whatever they're supposed to be producing, hormones or whatever it may be. Plants go through the same thing. So if it gets too hot, it'll start denaturing the enzymes it needs to function and do those cellular processes, and they won't be able to work anymore. Also, high productivity in the cold ocean waters due to upwelling. So we talked a whole lot about upwelling with El Nino and getting those nutrients pulled up. So you do need some of the cooler temperatures as well. CO2, lots of. That's why plants grow really, really well right next to roadways. They get loaded with CO2. And then obviously water. I can ask my friends how many plants I've killed because I forget to water them. All right, so a couple more things that affect them. Nutrients, any compound required by an organism to live, grow, or reproduce. NPK, do you guys have any idea what that might stand for?
NPK?
Yep.
Milk production kill-off.
No. Think back to your periodic tables. N is for nitrogen. P is for phosphorus. What does K stand for? No one ever remembers this because the word doesn't start with a K. Potassium, very nice. That one's always the tricky one. So all living things need those, nitrogen, phosphorus, potassium. That's what you'll see in a lot of fertilizers as well. Algal blooms, you guys saw a couple pictures of those last week, are often caused by an oversupply of a limiting nutrient. So you put a whole lot of this NPK or any one of those, and it runs off into a local river or stream, and it just allows everything, like all that algae, to just grow out of control. All right. That's an oversupply. We also talked about eutrophication. That's where that comes from. And herbivory, grazing by herbivores will lower productivity. So it's not just the grazing of them because they lose their leaves, but also the stomping as well will kill it. All right, so ideally the most productive ecosystems are higher temperatures, lots of water, lights, and nutrients. Obviously those temperatures can't get too high, but still need higher temperatures, nothing like today. So what would your least productive ecosystem possibly look like? Any guesses?
A closet.
Say it again, Leland.
A closet.
Cold is one. What else? Dry.
Like there's no water, and there's
No water.
usually no light.
Especially in a desert. And then we'd also be looking at a little bit of light. So think North and South Poles where they get 24 hours of darkness, right? They don't actually they have seasons during the year where they don't get any light. And then a lack of nutrients. So you guys have all seen all the different biomes for the most part. Here's kind of your primary productivity comparison, because obviously I don't have an x-axis of how good or bad the ecosystems are, or how they're able to produce energy for that bottom part of the food pyramid. So swamps, marshes, rainforest, temperate rainforest, coniferous forest, all in these top areas, especially these two. Guess what? These are usually warm and wet. So there's some right there. Aquatic ecosystems, estuaries, have insane amounts of productivity compared to anything else. Estuaries are kind of interesting too because that's where salt and fresh water meet. And so you tend to end up with a whole lot of stuff going on and a whole lot of productivity. All right, so humans use, waste, or destroy roughly a quarter to a third of the Earth's NPP. Yet we make up only 1% or less than 1% of the biomass of the Earth's consumers. So even though there's almost like 8 billion of us, we actually don't make up that much. But we use and abuse like 30% of it. So kind of a interesting little fact. All right, marine ocean producers. We saw some of this in your biome presentations. Microalgae, your phytoplankton. Everyone always hears about if you cut down the Amazon rainforest, we're going to lose a huge supply of oxygen, right? The Amazon rainforest produces, despite how many trees they have, produces very, very, very little oxygen. Almost half of what we breathe in comes from algae and phytoplankton. So that's actually our biggest producers of oxygen. Plants, you get all the seagrasses and seaweeds, bacteria, cyanobacteria, which was the first thing we know of that ever existed on Earth. And then chemosynthesizing archaeobacteria. Do you guys remember what chemosynthesizing is? Sorry, I was none of your biology teachers.
Chemosynthesizing is no, I was thinking of the wrong one. Never mind.
Okay, all right, no, that's good. So chemosynthesizing plants underwater that get zero light are able to still produce glucose. So they actually do it through like sulfur and methane and take that in instead of carbon dioxide. And then so it's called chemosynthesis because it's with chemicals, not with air. Some freshwater ones, algae, aquatic plants like the lilies, cattails. I'm sorry, if you guys have ever seen that YouTube video where that girl eats a cattail because she thinks like hot dogs grow in the wild and she ends up with that mouthful of cotton, it's so disgusting. They're cattails, they're not hot dogs, don't eat them. And duckweed, which is definitely a weed, but my fish at home love it. Bacteria, the cyanobacteria again.
Are all cattails filled with cotton?
Oh, hold on. Don't think I wasn't pulling up the video. I just have to wait for it to load.
All right.
If I have to witness this, so does everyone else. Like, as someone who used to work outside all the time, like, I knew what these were. Hot dogs are not the real world. Come on, YouTube. Be better than this. Maybe not. It is weird. Of course it would stop. There it goes. Try it again. Yeah, don't eat them. They're bad. They're disgusting. They don't taste good. No seasoning. They're not hot dogs. All right. Last slide. Unfortunately, this is where I would like to do a lab, but I can't. Light penetration in any general lake, not just Lake Superior, on an open water clear day. This goes for whether you're diving or doing anything like that with coral reefs. Hopefully you're familiar with the color spectrum, like the rainbow and wavelengths. You have really fast, very high, like, I don't want to say high pitch, that's sound, that's Doppler effect, but really high frequencies at purple, lower frequencies at red, and then you have like your infrared, which would technically be this way, UV over here, that's what gives me sunburns. As you go deeper and deeper in the water, light won't make it anymore. So one of the things I was actually just talking about with Mr. Delahoy, because he goes diving off the coast of Florida pretty often, is that when he takes his camera underwater with him, he has to have a special filter for being able to take pictures underwater, because you have red fish, but you go a few, 50 meters down or even less than that, you lose all the ability to see any red light. So you don't actually see it. And as you go further down, you start to lose the purple, you start to lose your yellows until you lose everything. And so there's a lot of investments that have to be made for like underwater photography or videography, stuff like that, where they have to add lenses or take away lenses to their cameras in order to get a more accurate picture of what it looks like. This has a big, algae and that type of growth for the bacteria and stuff. That's why you don't find it everywhere all over the ocean or everywhere all over a deep lake, because once you lose those greens and yellows, you can't produce any more photosynthesis. That's where that chemosynthesis comes in. So that's about all I had for you guys today on this. You have a few minutes if you need to finish up your nitrogen cycle assignment. I think I only got like 5 or 6 of those. You also have, I haven't pulled it up yet, you also have your DOL for primary productivity. The one thing I do want to say, because Daryl kind of reminded me about it earlier, if you do anything on AP Classroom after I put it into the gradebook, you need to tell me. It does not alert me. It doesn't tell me, oh, hey, Keenan went back and took DOL number 4. I will have no idea unless you tell me to go back and look for it. So keep that in mind. If you do the DOL for today, then and you go back and do maybe one that you forgot last week, then let me know so I can update your grade, because otherwise I'll never see it. What's up, KK?
So, do you grade before Saturday night, or like Saturday morning for the DOLs?
It depends, to be honest with you. With you guys being asynchronous on Mondays, I've been doing a majority of my grading on Monday. And then sometimes I try and catch it throughout the week. But yeah, like the DOLs and stuff, I don't look for typically until Sunday or Monday.
Okay, because I did my 2 DOLs throughout the day on Saturday.
Okay, so if you see a discrepancy between the grade book and what you've done on AP Classroom, just let me know and I can like double check it and fix it too.
Okay, thank you.
Gotta put some seasoning on them cattails. Hey, Miss P.